Welcome back to the lecture of engineering mechanics. In this video, we'll discuss dynamics. Okay, in the first part, we have talked about rectilinear motion. In this portion, we'll be talking curvilinear motion. Okay, so what is curvilinear motion? In the previous video, we discussed about rectilinear motion. That means the motion is along the straight path. Here, the motion will be along a curved path. That's called curvilinear motion. Okay. In the rectilinear motion, what is rectilinear motion? This one is a line over the straight path the object was moving. Suppose this one is the object, the object is moving in this direction, but in the rectilinear motion what will happen? It will be a curved path like this. Okay, this is a curve, so this object will move like this here, then it will come to this position, then it will come to this position. So the path is a curve. In the translatory motion or rectilinear motion, the path is a straight line. Here the path is, see what I'm saying, the object is moving along a curved path called curvilinear motion. That's the definition. We are going to discuss the curvilinear motion in detail. We will analyze this curvilinear motion. Okay, to analyze what are the parameters required. Okay, we will see one by one. Now, before explaining the concept of curvilinear motion, I want to tell you see, this one is moving along the curve. Okay, what I'm saying, if the velocity will be in this direction of this object, will the object will move along the curve? Not at all. If the velocity is in this direction, can the body will move along the curve? Not at all. So the velocity vector, okay, the velocity vector must tangent to the path. Okay, whatever the path, the curve path, this will be the vector, velocity vector. Okay, the object will move along the path, then only the contact between the object and the curved surface, there will be contact, so the motion will be possible. Otherwise there will be loose of contact, you cannot say it's a curvilinear motion. Okay, so when for the curvilinear motion or any motion, I'm not, see here also the velocity is straight, that's also along the straight line, along the path. Okay, so the motion is possible only when the motion of the object is possible only when the velocity is along the path. Okay, so from here I can write for any motion, not just rectilinear or curvilinear, I'm saying the velocity of the particle because I'm considering particle, then we'll talk about a bigger body. Okay, so the velocity of particle is always tangent to the path. What does it mean? I have already explained it. The velocity vector will be tangent to the path. Okay, whether it's a rectilinear motion or curvilinear motion. See the difference between curvilinear motion and rectilinear motion. I can say the rectilinear motion is nothing but a curvilinear motion having what? Having the radius is infinity. What I mean, radius of the path is infinity. I'm saying this is also a curved. That means what I'm saying, see, if I'll draw a circle like this, okay, I'm considering, suppose this portion, I'm just considering this portion of the, if I'll zoom it, okay, if I'll zoom this portion, I'm zooming, okay, so see this portion, as you can see, this is nothing but a straight line. Okay, so What I'm saying, the rectilinear motion is nothing but a curvilinear motion. Okay, whatever concept will be for the curvilinear motion, the same concept will be for the rectilinear motion. We have already discussed rectilinear motion. Now we'll discuss curvilinear motion. Okay, see, this is a curve path. The curve will have a center. Okay, this is the center for this portion of the curve. For this portion of the curve, the center will lie somewhere here. Okay, so it's having some radius, or here also some radius from the center. Okay, so any curve having some radius, because the curve is nothing but the part of the circle. Okay, curve is nothing but a part of the circle, so it will have some radius. Here what I'm saying, this one is a generalized curve. That means the radius is not constant throughout. The radius is varying from location to location. Okay, if you talk about this one, at every location, okay, the radius is constant. So whenever the radius is constant, the curvilinear motion will be called as circular motion. Okay, this is the special case, circular motion. So the particle is moving in a curvilinear motion that having radius which are varying, but in case of curvilinear motion, the radius is constant. If the object is like over here, and it will travel like this. Okay, this is the special case of curvilinear motion. We'll discuss curvilinear motion, then we will get the idea what are the parameter, okay, for discussing curvilinear motion. Now I'm saying another statement. Since, see, here also the tangent to the path, that means the radius, this one is the radius. So radius and the velocity vector, over here there will be an object, so it will have the velocity vector like this. So the velocity vector and the radius vector, everywhere the velocity vector is always perpendicular to the radius. Over here also the object will be like this, the velocity vector along the path. So the tangent, this is the velocity vector which will also perpendicular to the radius everywhere in curvilinear motion. Okay, the here what I'm saying, the in the rectilinear motion the center is at infinity, so the radius is nothing but a vertical line and the radius is perpendicular to the velocity vector here also. So I'm writing the velocity vector, the velocity vector is always perpendicular to the radial vector. Getting my point? So this one is the velocity will be along the path, and the second statement is saying the velocity always perpendicular to the radial vector. Okay, now actually what is velocity? In the rectilinear motion, we simply say the rate of change of displacement is known as velocity, but the actual definition of the velocity we'll discuss. So in circular motion, what is the important thing? The radius. Okay, the radius is constant. See, from these two statements we can observe, see, velocity is a vector quantity. It's a vector quantity. Vector will have magnitude as well as direction. So whenever the particle is moving in a curved path, the velocity is always along the path. That means suppose this particle is moving at a velocity of 5 meter per second, here also 5 meter per second, here also 5 meter per second, but the direction is not constant. In curvilinear motion, the direction is keep on changing point to point. Over here also, this is the special case of curvilinear motion. Here also, from this point to this point, the velocity vector was like this. At the point over here, when the particle reaches here, the velocity vector is like this. Okay, so the direction keep on changing. So the velocity vector direction keep on changing. Magnitude may constant or may not constant. That will depend situation to situation, but the direction is always changing in curvilinear motion. But in case of rectilinear motion, what was we are saying, we are not considering the direction change. Only we are talking about whether it's in positive x-axis or negative x-axis, because the path is a straight line. There was not much more changes in the direction. There is only we are talking about the magnitude changes. Here in curvilinear motion, we have to consider both the magnitude changes and direction changes of the velocity vector. Okay, this one is the velocity vector. Now we'll talk about acceleration. See, before that, if I will talk about for the curvilinear motion, this one having an radius of r and velocity v. So the definition in case of circular motion, okay, in case of circular motion, whenever any particle is in circular motion, the velocity vector is nothing but the cross product of position vector into omega vector. So what I'm saying, here is the r vector, okay, this one is lying on the plane. There will be an omega vector, okay, there will be an omega vector which will be along this axis. There will be an axis perpendicular to the plane passing through this point over here. So these two are in a, if you consider in a plane, then the velocity vector will be perpendicular to the both the vectors. That is the result of the cross product. Okay, here you are getting a vector as a result, because in the dot product you are getting a scalar result. In the vector product, that is cross product, you are getting a result as a vector. So now we will discuss what will be the acceleration. We discussed how the magnitude will vary, because the direction is keep on changing point to point, and the magnitude will depend upon the situation. Now I'm going for the acceleration. See, the acceleration is nothing but what we have discussed. It's the rate of change of velocity with respect to time. The velocity can change with respect to magnitude. If there is a magnitude change, then also there will be acceleration change. Okay, if there is a change in direction of the velocity, there will also an change in acceleration. Okay, so there will be change in acceleration. Getting my point? So we have to consider both magnitude variation and direction. If there is any changes in direction or any changes in magnitude, we have to consider both. Then only we will be able to get the actual value of the acceleration in curvilinear motion. In case of curvilinear motion, the acceleration can be classified into two. There are two types of acceleration. One is responsible for direction change, and the other one is responsible for magnitude change. Okay, the first one is called tangential acceleration. The second one is called normal acceleration or radial acceleration. Okay, normal acceleration, it's an, this one is, sorry, acceleration subscript n, that's normal acceleration. Over here this is at, the translational acceleration. Okay, there are two types of acceleration. The tangential acceleration is responsible change in magnitude changes of the velocity. Okay, whenever there will be change of magnitude, whenever there is a change in magnitude, there will be changes in tangential acceleration. Whenever there is a change in direction, there will be change in normal acceleration. So the acceleration is nothing but the summation of tangential acceleration and normal acceleration. So the actual magnitude of the total acceleration, this one is the total acceleration. Okay, the total acceleration have two parts. The first one is responsible for magnitude changes of the velocity, and the second one for the directional changes. These two acceleration have some characteristics. You have to understand the characteristics of tangential acceleration as well as normal acceleration. Now what are the characteristics? See, I'm writing over here. First, the tangential acceleration, which is nothing but a subscript t, that is represented like this. These are the vectors. I'm removing vectors, that means I'm talking about in a particular, okay, particular case. So the other one is normal acceleration. Normal acceleration a subscript n, okay. These are the two acceleration, okay, which will give the total acceleration of the object. So the first characteristics we have already discussed. That means the at is responsible for change in magnitude, and the normal acceleration is responsible for change in direction. Direction of what? I'm talking about changes in velocity, okay, because the acceleration is nothing but the rate of change of velocity. So if there is a change of magnitude of the velocity, that means we will say there is an tangential acceleration. If there is a change in direction of the velocity vector, we will say there is a normal acceleration. If there is no changes in magnitude of the velocity vector, we will say the tangential acceleration is zero, okay. If there is the direction is not changing, we will say the normal acceleration is zero, okay. Since the velocity vector here, it is depending upon the magnitude, okay, the tangential acceleration is responsible for change in magnitude. So we know the velocity is always along the path, so this one will also along the path. So I will write the at vector, the at and v, sorry, I will write in this way: the tangential acceleration is collinear with the path, or I can say with the velocity, okay, with the velocity vector. Okay, how the direction is changing? See in this slide, the direction is changing because the velocity vector is perpendicular to the radius. If the radius keep on changing, then the velocity will also change. So in this one, I'm saying the tangential acceleration is collinear with the velocity vector. I'm not saying in a particular same direction or opposite direction. If the direction is same, from this statement, if the acceleration at and the velocity vector v in the same direction, in this situation what will happen? The magnitude will increase, okay. Then in this case, the magnitude of the velocity vector will increase. If the velocity vector is in this direction and the acceleration is in opposite direction, what will happen? The velocity, the body is moving in this direction, but the acceleration in the opposite direction, so the magnitude of the velocity will decrease. Getting my point? So these are the interpretation from this statement. And one more point will be like this: if the I will write what? If the velocity is constant, if the velocity is constant, there is no changes in velocity, okay, the velocity is uniform. Whatever we have studied, the uniform motion, that means the acceleration was constant, okay. So I'm saying if the velocity is not varying, then acceleration, tangential acceleration will be zero, okay. The body is moving with a particular velocity. So these are the three characteristics of the tangential acceleration. The normal acceleration, the change in this one is responsible for change in direction, okay. The second one will be the direction. I will write the normal acceleration, okay, an. The normal acceleration is always directed along the radius of the curved path. Okay, it is always directed towards the center of the curve. Okay, so this one sometimes called as center seeking acceleration. Center seeking acceleration, because it is always directed towards the center, that's why it's called center seeking. Okay, this one, or this one also called the centripetal acceleration. That means these are the terms which are used with respect to normal acceleration. Okay, this one is responsible for changes in direction of the velocity vector. Okay, direction of the velocity. Here the velocity vector, the normal acceleration, here what was the direction? The normal tangential acceleration was collinear with the velocity vector, but an is perpendicular to the velocity vector or path. Velocity vector. Okay, this one is the another statement. Now I'm explaining you the curvilinear motion. See, suppose the tangential acceleration, which is responsible for change in magnitude. So at is nothing but dv by dt. Okay, I'm saying if the uniform acceleration, okay, for the uniform acceleration, if the acceleration is uniform, that means the force is constant. In this situation, we know v is equal to u plus at. For rectilinear motion, we have already discussed in the previous video. Now this one is valid for which one? This one for rectilinear motion. Okay, but for circular motion or curvilinear motion, circular motion means I'm saying the curve having a constant radius everywhere. Okay, so here the at will be like this. At is r alpha. The formula is like this. At is equal to r times alpha. Why I am writing this? See, the at will be written as d by dt of velocity vector. For the circular motion, the velocity vector is nothing but cross product of r vector into omega vector. Okay, so this is the formula. I can write v is equal to r omega in simple term. The velocity is nothing but the product of r into omega whenever the sine theta, sine 90 degree is equal to 1. We know, because if you just open this, solve this r vector into omega vector, r vector cross omega vector, you get r omega sine theta. If the theta is 90 degree, then sine 90 degree will be 1. So this one is the case in case of circular motion, because in the circular motion the radius is same everywhere. See, this is the circular motion. Everywhere there is a radius and the velocity vector over here, and the object is rotating in the omega about this point. Okay, there is an axis. So r vector and omega vector are perpendicular to each other. So you are writing v is equal to r omega. Getting my point? So if in this equation, if I'll put v is equal to r omega, what we will get? D by dt of r omega. In circular motion, r is constant. I'm taking out. So d omega by dt. This d omega by dt is nothing but alpha. So I can write r alpha. So the tangential acceleration formula I got to be as r alpha. R is the radius and alpha is the angular acceleration. Okay, we will discuss the terms related to what is angular velocity, angular acceleration in detail. Before that, I'm just deriving this one. Okay, the d omega, omega is nothing but angular velocity, so the rate of change of angular velocity is nothing but rate of the angular acceleration, that is alpha. So you got the tangential acceleration formula as r alpha, at is equal to r alpha. This one you need to remember. So in this situation, whenever the omega will be 0, see, whenever if omega is equal to 0, if omega is equal to 0, that means the object is rotating or the particle is rotating at a constant angular velocity. In this situation, what will happen? The derivative will be come out to be 0. In this situation, the at, the tangential acceleration, will be 0. Okay, so omega means, whenever there is a circular shaft in the engineering application, there is a circular shaft rotating at an angular speed of n rpm, rotation revolution per minute, n rpm. For this situation, omega is written as 2 pi n divided by 60, that is the radian per second. This is the formula for omega in case of a shaft is rotating at an speed of n, okay, having unit as revolution per minute, rpm. Now we got the value of tangential acceleration, and we know the direction of the tangential acceleration. It is nothing but it is collinear to the velocity vector. Now we'll derive what will be the an value. See, the an value is nothing but v square by r. You can write v is equal to r omega, so you can write r omega square divided by r, so it will nothing but r omega square. So you need to remember an is equal to v square by r or r omega square. Okay, this is the formula for normal acceleration. You have to remember this one and this one, small r. Okay, everywhere you take as small r. This is the radius. See, in a curved path, suppose I'm taking a curved circle like this. Okay, this is a circle, so I'm saying this one is the tangential acceleration. Okay, and the normal acceleration is always towards the center. Okay, this one is an. These are perpendicular to each other. So from the parallelogram law, we know the total acceleration, the resultant of these two acceleration will be nothing but root over of at square plus an square. This is the formula for calculating total acceleration of an particle or object which is in curvilinear motion. Okay, whenever the particle is in a curve motion, that means the particle will have two types of acceleration. Number one is called tangential acceleration, which is responsible for changes in magnitude. Okay, magnitude. And the normal acceleration is responsible for changes in direction of the velocity. So these two formula you have to remember. At, the tangential acceleration, is equal to r alpha, which is collinear with the velocity vector, and the normal acceleration an is equal to v square by r is equal to r omega square. This formula I can also derive at this point of time, but that's not required. Okay, if you have interest in the detailed syllabus, if we will make a complete theoretical video, in that syllabus video I can make a derivation of this normal acceleration, how this formula will be derived, but you should remember just r omega square or v square by r. Okay, and the other formula is nothing but v is equal to r omega. V is equal to r omega. Okay, this is the formula. Three formula you have to remember. This one, and the upper one, tangential acceleration. Since we have started the discussion of circular motion, let's complete the circular motion. Okay, then we will discuss the terms which will be related to curvilinear motion, like angular velocity, angular displacement, angular acceleration, what will be the equation of motion in case of a curvilinear motion. These things we'll discuss. Before that, we will see, I'm drawing a diagram. Suppose this is a straight line. Okay, over here what I'm saying, a particle is projected at this direction, okay, at an angle of theta. This is the velocity vector of the particle. This one is the horizontal surface, okay, this is the ground. I'm standing over here at this point of, and I'm throwing a ball in this direction. So what will be the chord of the particle? This is the particle, okay. So this is thrown at an angle of theta radian, okay. Now I'm drawing the project, okay, the path which will be covered by the particle. See, the path will be like this. The object will move like this. It will go somewhere over here, then it will come down to at this position. So what will happen? This one will be the final velocity, okay. So if the object is thrown at a velocity of u, okay, at making an angle theta, this will be the path. This will be the path of the object. This path will be like called a parabolic path, okay. The parabolic, the chord will be a parabolic. It's not a circle. And this motion is known as projectile motion, okay. Projectile motion, because the object is projected into the air at certain angle, and we got this as the path of the object. Now I'm marking some points like this. This one is a point, okay, and the top one another point. I'm marking 3 points. Can you discuss whatever we have discussed till now? Can you just show over here? So the point, this point I'm writing, this one is A, this one is B, this one is C, this one is D. So what will be the velocity vector at point B? It will be tangent to the curve, okay. So this one will be nothing but tangent to the curve. Getting my point? That will be the velocity vector. This is nothing but velocity at the point B. What will be the velocity at point C? This one will be the tangent. Here also this one will be tangent. So I can write this is the velocity at point C, this is the velocity at point D. If this is the center, okay, this is not center because it is not a circular path, because point to point there will be different center for the curve. So now I'm trying to show the acceleration of the points, okay. So whenever the object will be at point B, there will be two types of acceleration, because the object is moving in a curved path. The first one will be a tangential acceleration and the other one is normal acceleration. We know normal acceleration is towards the center, okay. Each particle, this particle having a mass m, okay, m is the mass. So the mass will be always towards the gravity, towards the center of the gravity. So I'm just showing the weight, okay. These are the weights, downward direction, okay, everywhere. So this is nothing but mg, mg, this one is mg, this one is mg. These are the weights in the downward direction. Now if I will just resolve the velocity at all the point in horizontal and vertical direction like this one will be the same. There will be no velocity component because the BC is in horizontal direction, so there will be no component. So here will be one and the other one will be like this. Here also there will be two component, one is will be horizontal, other one is vertical. So I can write, since this one is theta and this angle, since the path is not a circle, the angle keeps on changing. This one is alpha, then this one is called angle made is beta. Then I can write this is nothing but Vb cos alpha, this one Vd cos beta, the upper one Vb sin alpha, here will be Vd sin beta, this is Vc, okay, only horizontal component. So at the top point in the projectile motion there is no component in the vertical direction. So this is the actual velocity I am resolving into two components, that is horizontal and vertical. The horizontal is responsible for the motion in the horizontal direction and the vertical velocity is responsible for the changes in height. That means the ball is going in upward direction and downward direction. This is the responsible by the normal component of the velocity. Now at this situation, can I draw the velocities, the acceleration? See, this one will be towards the center, okay. Since I'm not writing, I'm removing the weight, okay, I'm just showing the direction of the acceleration, okay. So since this one is g and here is the angle called alpha 90, so this one will again be alpha, so this one will be g cos alpha, this one will be nothing but the normal acceleration which is perpendicular to the velocity vector. We have already discussed the normal acceleration an is along the radial direction towards the center, or we can say it is perpendicular to the velocity vector Vb, okay. Here also the normal acceleration will be like this, okay. Since this is beta, this is will be 90 minus beta and this angle will be beta, so it's g cos beta is nothing but how much? An, okay. At this point of time, at this stage, whenever the object is at point C, the normal acceleration will be nothing but g will be the normal acceleration, okay. The g value will be normal acceleration which is perpendicular to the velocity vector. All the normal acceleration are perpendicular to the velocity vector, okay. All the normal acceleration, this one is also perpendicular, getting my point? And you know, I have discussed in the starting of dynamics there is something called inertia force. Inertia force having magnitude as ma, mass into acceleration in the opposite direction. Direction is opposite to the acceleration, and the point of application, you know, at the center of gravity of the object. So the point of application, these are the characteristics of the inertia force we have discussed. Now I'm zooming this one, okay. So see carefully, in a dynamic object, I will write here, in a dynamic, whenever dynamic condition, in a dynamic condition, corresponding to each acceleration, okay, corresponding to each acceleration, there will be inertia force. If you have 2 acceleration, there will be 2 inertia force. If you have 5 acceleration, there will be 5 inertia force, okay. So corresponding to each acceleration, there will be an inertia force. In this video, we discussed the direction of the normal acceleration at every point. So this is the normal acceleration. So there will be an opposite, in the opposite direction, there will be an inertia force m into an, which will be nothing but mg cos alpha. Here also there will be an inertia force. Here also there will be an inertia force. Okay, so mass into acceleration, that's all. If there will be a tangential acceleration along the vb vector or in the opposite direction of the vb vector, because the tangential acceleration at is always collinear to the velocity vector. The velocity vector is vb vector. See, as you can see, the vb vector in this direction, the vb vector is in this direction, so the acceleration will be in the same direction or in the opposite direction, but collinear to the velocity vector. Getting my point? Here also the tangential acceleration will be along the velocity vector. Over here also the tangential acceleration will be along the velocity vector, but the normal acceleration always perpendicular to the velocity vector. Over here, this one is the velocity vector, this one is the normal acceleration, these are perpendicular to each other. Okay, so this statement is very important. Okay, corresponding to each acceleration there will be inertia force. So what is the concept behind this? See, suppose what I'm saying, suppose you have standing over this point and you have a ball. Okay, you have this ball, you are standing over here, you are a man. Okay, you are standing over here and the ball is connected with a string and you are rotating about the horizontal plane. Okay, you are rotating over your head like this, you are just revolving this one. What will happen? Since this one is in curvilinear motion, there will be two types of acceleration acting. The first one will be towards the center, that will be the normal acceleration. Other one will be like this one is the tangential acceleration. Corresponding to tangential acceleration there will be an inertia force, here will be also inertia force. This inertia force is nothing but centrifugal force, which is responsible for making the motion in a circular path. Okay, whenever the string will break, the object will not, the object is moving in this sense. Okay, whenever the string will break, this one will not go in this direction or in this direction, this one will go in a particular direction like this, because of the normal acceleration and the mna, that is the force in the direction of the force, because the motion is always along the force. So here is the centrifugal force, mass into normal acceleration, and here another force will be the torque. Due to the torque application, the motion is in this direction. So over here in this particular direction the object will move whenever the string will break. Okay, this is the concept of inertia force, centrifugal force. Now we will discuss the terms which are related to, I will discuss the terms. Okay, we'll start as we have discussed in the rectilinear motion. Here also there are a first term called angular displacement. What is angular displacement? See, this is represented as theta, angular displacement. This is nothing but the angle curved by a particle in circular motion. Suppose this one is the particle is moving in this curved path, so the angle, whatever angle will be made by the particle, this angle theta is nothing but the angular displacement. Getting my point? So the angle you got by the motion of the particle in a curved path, okay, that's called angular displacement. And the second term is not, the unit of this one is radian. Okay, because you know 180 degree is equal to pi radian, you can convert whenever required. The second term called angular velocity. This is represented as omega. What it is saying? The rate of change of angular displacement, the d theta by dt, these are the vectors. I'm just removing the vector, that means I'm talking about a particular direction. Okay, the omega is nothing but the rate of change of angular displacement is the angular velocity. Okay, the unit is radian per second. What it is mean? The object is moving in a curved path. Okay, this is the curved path. So the time to time the angle is changing. In the first 5 seconds you got 30 degree. In the second you got 20 degree. In the next 5 seconds you are getting 20 degree angle. So the angle you are getting keep on changing. So the displacement is changing. So the change of the displacement with respect to time is known as angular velocity. Okay. So what is angular velocity? It is the rate of change of angular displacement. Okay, the direction of omega is perpendicular to the plane. See, if this one is the path of the particle, this is the particle which is moving in the circular path. So this one is the radial vector, this one is the velocity vector tangent to the path. Okay, you know, the velocity vector is nothing but the cross product of position vector into omega vector, that is the angular velocity vector. So what I'm saying, the r vector and omega vector are perpendicular to each other. Here see, the r vector and omega vector are perpendicular to each other. That means they are in a single plane. And I'm saying the r vector is also perpendicular to the r vector. That means the omega vector is along an axis passing through this point in this sense. Okay. So in 3D, if you will draw an coordinate axis like this, okay, so here this one is the radial vector, this one is the velocity vector, okay, in the downward direction. So I'm not taking, so here is the point I'm showing, this point about this axis, the angular velocities of the object. Suppose this is the circular motion of the object. Okay, this is the radius and this is the velocity. So the omega will be like this. Okay, so the omega is like this. Getting my point? The omega vector, the angular velocity vector, is perpendicular to the plane over which the motion is happening. Okay, so omega, direction of the omega is perpendicular to the plane. You know how to find the direction of the cross product, because in the first video of moment I have discussed the right hand thumb rule. You have to align your right hand along the position vector, then you have to rotate towards the force vector, you will get the moment vector. Similarly, because the moment vector is nothing but the cross product of position vector into force vector, we have discussed already. You have to align your right hand along the position vector to the force, then you have to call your finger, rotate your finger towards the force, then you will get the direction. The thumb will direct the axis about which the moment is moment vector. Here also you have to align your right hand in the position vector and you have to rotate your call finger towards the which one? Omega, then you will get the direction of the velocity vector. You do the opposite. See, you know the velocity vector, you know the r vector. So I'm saying the r vector, this is the result by the right hand thumb rule. If I'll explain you like this, see, this is the circular motion. Okay, this is the center, here is the point, over here suppose this is the velocity vector and here is the r vector. Okay, I'm saying the omega is in this direction. If you want to calculate the omega, direction of the omega, what you will do? You have an hand. So I'm saying the v vector is nothing but the cross product of r vector into omega vector. See, omega vector is perpendicular to the plane, you know. So how will calculate the direction? You just do, suppose this is the radial vector, this is the velocity vector, okay, and you are saying this is the omega vector which is perpendicular to the both. So I'm saying what? This one is the radial, this is the velocity, this is the omega. So the cross product of the r vector and omega vector will give you the velocity vector. So I'm saying you just align your thumb. Okay, this is the result, because the result of the cross product will be shown by the thumb of the right hand. So align your thumb. Okay, align your thumb in the velocity vector direction, because you know the velocity vector direction, wherever, in whichever direction the object is moving, you know this one. You want to know what is the direction of the omega, so you align your right hand thumb in this direction, and if you just do your right hand and thumb is directed towards the down, right, towards the down, okay, in the vertical down direction. And you just align your, you just, what I'm saying, now see, you just align your hand like this, okay, the thumb of the your right hand in the upward direction, and you just rotate. This is the alignment of your right hand, this is the r vector, and after aligning, you just rotate your, the forefinger of your hand towards in this direction. You will get the thumb is directed towards the out of the plane, okay. At this point you have thumb, these are the four finger, you are rotating like this, okay, towards the velocity vector. You will get a thumb is directed towards the out of the plane, that is nothing but the omega vector. Getting my point? So by right hand thumb rule you can find the direction. Simply, you don't need to use anything, you just see this is the direction of the radius, okay. Which one? This one is the direction of the radius and the velocity is in this direction, so the object will rotate in this sense, that is nothing but clockwise. If the velocity vector directed upward, then the object will rotate in this sense, that means it's a counterclockwise. So the direction is will be clockwise or counterclockwise, that's all. You don't need to apply anything. So the, this is the angular velocity. If you talk about what is the average angular velocity, that will be nothing but the total change in angular displacement divided by total time taken. That is nothing but average angular velocity. Average means the total divided by the total time taken, okay. Now we will go for the acceleration, okay. The third one called angular acceleration. This is represented by symbol alpha, that's called angular acceleration. Now I'm taking a circle, okay, this is the circle, see, this is the path of the particle. Suppose this is an object which is rotating in the circular path, okay. What will happen? Why it is rotating? Because there is a torque applied on this, so this is the omega, because the velocity is in this direction, okay, and the acceleration also in the same direction, the acceleration also in the same direction, the velocity vector and the tangential acceleration is in the same direction, and the normal acceleration is in the opposite direction. Getting my point? So these are the thing we have already discussed. Now I'm just talking, this is the tangential acceleration, normal acceleration we don't need to consider over here. I'm just saying the tangential acceleration. So the tangential acceleration is responsible for change in velocity, magnitude of the velocity. So here what is happening, the magnitude is changing due to this one at. So the angular acceleration, the definition of angular acceleration alpha is nothing but the rate of change of angular velocity with respect to time. So the rate of change of angular velocity is known as angular acceleration, having an unit as radian per second square. Similar to the rectilinear motion, I can write like this: alpha is equal to d omega by dt. If I'll multiply in the numerator d theta, in the denominator by the d theta, so you will get d theta by dt is nothing but omega. So I'll write omega into d omega by d theta. This is also one formula for angular acceleration, okay. You know, at we have discussed, at is equal to r alpha. This is the use of the angular acceleration, okay. If you know omega, theta, whatever, from the formula, these two formula, you can calculate alpha, okay. Once you know alpha and radius, you can calculate tangential acceleration of any object, okay. These are the formula you need to remember. There is another one that's called, see, we have talked about net force is equal to mass acceleration, Newton's law of rotation. That means in case of rotation of any object, there is a law called net torque is equal to net force is equal to mass into acceleration. Here net torque is equal to I, that is the mass moment of inertia, that is the mass moment of inertia into angular acceleration alpha. So net torque is equal to I alpha. From here also there is an application of this term angular acceleration. This one is used in the rotation. We will discuss in whenever we will talk about rotational part. Okay, you just, I'm saying the application. Here is an application of angular acceleration. Here also there is an use of angular acceleration. Why an object is rotating in a circular or in a rotation is rotating? Why any object will rotate? Because of the torque. That means the moment is nothing but the rotational effect. Okay, so the moment is the cause. Moment means the torque. Moment is nothing but torque. Okay, the same alternative term used. So due to the torque applied on any object, the object is rotating. If the torque is constant, there will be two situations. If the torque is constant, if the torque is not constant, okay, if the torque is constant, that means alpha will be also constant, the angular acceleration will be constant. Here angular acceleration will not be constant. If the angular acceleration is not constant, then we will say it's a non-uniform rotation. Non-uniform rotation. Here this one will be called as uniform rotation. Okay, similar to the rectilinear motion, uniform rotation. For the uniform motion, we have a set of equation like s is equal to ut plus half at square, v is equal to u plus at, v square is equal to u square plus 2as. Similar equation we have for the this one. Okay. So what I'm saying, this is the angular motion, alpha is the acceleration. Okay. So similarly, the alpha is nothing but rate of change of omega, d omega by dt. The rate of change of angular velocity is the angular acceleration having an unit of radian per second square. You can just multiply d theta by d theta in the numerator and denominator, you got this formula. Okay, then the Newton's law of rotation is simple, like net force is equal to mass into acceleration. Like net force is equal to mass into acceleration, you replace net force with the net torque. This is the inertia in translational motion, this is the inertia in the rotational motion. So m will be replaced with mass moment of inertia, a will be replaced with alpha. So net torque is equal to I alpha. So if the torque is constant, then alpha will be constant. If torque is not constant, alpha will be not constant. It will be non-uniform motion. If non-uniform motion, you have to use the general definition like alpha is equal to d omega by dt or alpha is equal to omega d omega by d theta. If it is a uniform motion, you can use these are the four equations like v is equal to u plus at. So you have to replace this one. V will be replaced with omega, acceleration will be replaced with alpha, s will be replaced with theta. These are the terms related to angular motion. Okay. The last term, that is the fourth one, called angular momentum. That is nothing but it is represented as h. The linear momentum p was mass into velocity. Here it is h is nothing but inertia. This one is the inertia in case of rectilinear motion. This was the velocity. Here inertia, mass moment of inertia into velocity will be omega. So I omega is the angular momentum. Getting my point? This is the formula. So for a particle, if I will replace omega, because we know what B is equal to R omega. Getting my point? So for a particle, sorry, I'm saying for a particle, if this is the center and the particle is rotating in a circular path, for the particle, you know, if it is at a distance of r, and this particle having a mass of m, then the mass moment of inertia is nothing but mr square, which is similar to the formula of mass moment of inertia of the ring. Okay, mr square. So I can write mr square omega is the angular momentum. Okay, or if you replace like this, you can write mrv, because v is equal to r omega. Okay, or you can write mv into r, mv into r. That means this one is the linear momentum, this one is the radius. Okay, so if you are multiplying with a perpendicular distance radius, that means the angular momentum is nothing but the linear momentum into perpendicular distance. So the angular momentum is nothing but the moment of the linear momentum. That means the moment of the linear momentum is known as angular momentum. Okay, if you know the angular momentum, a linear momentum, p is equal to mv, you just multiplied with the perpendicular distance, that is nothing but radius, you will get the angular momentum. Getting my point? So similarly, since we have discussed net torque is equal to I alpha, there is, you can get some principle like this one. Impulse is equal to change in momentum, so you can get rotational impulse is equal to rotational angular momentum. So I can write similarly, if you just do some mathematical calculation, you got this is the rotational impulse, which will be equal to I omega final minus omega initial. Similar to this is the change in momentum, the change in angular momentum, this is the rotational impulse. This will be an principle in case of rotation, similar to the rectilinear motion. Okay, this is all about the concept related to the motion along the curve. Okay, so remaining part of the dynamics we'll discuss in the next video. Okay, so thank you for watching. In the next video we'll discuss the other part of the dynamics.